So we are continuing on the discussion of random phase cosine. So we had an example called random phase cosine, and we are continuing from that topic. So what was that example? Well, I'm assuming that I have a random process, emphasize the random process by this tilde, which is in this form. Amplitude A is constant, frequency is constant, and this is the process variable t, obviously. Only thing that is random, that is generating this process is phase. So you may consider that the phase at t is equal to 0 is randomly selected when this is not present over here from this distribution. Okay? So if you also know the phase value, starting phase value, then this becomes a deterministic signal, isn't it? So every realization, every peak from this distribution becomes a realization, and that's a deterministic function of time. But right now I am thinking about, how this is picked in terms of uniform distribution, and what about its consequences. Okay. Last time we have discussed joint PDF description of it. So today we are discussing moment descriptions. So let's see whether moment descriptions are easier or not. A. So let's try to calculate the mean function of this process. Okay. So it is denoted as mu x of t, and this is the expected value of this random process evaluated at a specific time. If you want, I can write t1 over here just to emphasize it. So if you evaluate it at a specific time, this becomes a random variable. Then you are taking the expected value over that, whatever that random variable is, x of t1. But we have found the density of x of t1, joint density even x of t1 and t2. But right now I only want to calculate the mean of it. And you see inside the argument of the expectation, there is only one random quantity theta. And then I know that this is distributed with this. Okay. Then I can write this one as, well, from 0 to 2 pi, 1 over 2 pi, a cosine omega t plus theta d theta. Do you agree? Because it is uniformly distributed in this interval. This is the interval. This is the normalization value to make this area under this uniform distribution 1, and I have such a case. Well, just be careful when you're integrating something. Most of the time, in many other courses, you're integrating over time. You calculate, I don't know, maybe average power, things like that. Okay? But this is not a time average. Be careful, this is theta average. Okay? So I'm taking the average over this theta values, d theta. So what do I mean by this? For a given number like this, so I'm integrating a cosine waveform. Let's say this is theta. It starts from a value, and then it just comes up to this same value in 0 to 2 pi. Okay? So this is this function. So it starts from, let's say, a cosine omega t at this point when theta is equal to 0. So this is obvious, I know, but don't make a mistake over here. So think about it, this is just a constant. So I'm integrating over a full period of cosine. When theta is changing in between 0 and 2 pi, I'm integrating a full period of the cosine, as you see, and then I get 0. Okay? This is equal to 0. Of course, you can evaluate this integral by saying that, well, this is sine evaluated at these times, and then you can subtract. But don't do things like that. Try to understand the integral. So this is just a constant. I'm integrating when starting from theta is equal to 0 up to theta is equal to 2 pi. This is just a constant. So this is the full period with respect to this theta. Area under the full period is equal to 0. So this is the end of this discussion, end of the mean function calculation. So this is some, you may say, calculus. But what we have done is, do you remember we have evaluated this density last time? It was, we have sketched this. So it was limited to A and minus A. So it has a shape like this. Okay. So this is the density. This, let's say, evaluated at T1. Okay. It has a density in this form. And you see that this density is symmetric with respect to this origin as expected. Okay. So what is the mean value of this density? It is 0. Well, we have found that mean value without evaluating this random variable. Okay. That was the easy thing about expectations. So this step is such an innocent step, simplifies our calculations significantly. So I get this 0 without even calculating, this density. I just calculated from the definition of this random process. Now, let's see second order descriptions. For example, autocorrelation description, autocorrelation function. So what was this? This is defined as, now I have, this is second order, two random variables. And their product is under expectation. So I need the joint density. Okay. But as we have said, I don't want to find the joint density because it's complicated. I will use the process definition. So this becomes a square cosine omega t1 plus theta cosine omega t2 plus theta, and that is it. So only thing that is random inside of this expectation operator is theta. So then I have to calculate this. So the problem is almost like solved. I have to do this operation. So how can I do this? Let's take this out for the sake of simplicity. A square. Then can I write this as divided by this. These are cosine 2 theta formulas. Okay. So if I call this, for example, alpha, something I don't use, this is alpha plus beta. This is alpha minus beta. Maybe you can remember. There is a 1/2 factor over here, but you remember it in general like that. 2 times cosine alpha times cosine beta is equal to cosine alpha plus alpha minus beta. Okay, that is this one. Okay, now I can take this 1/2 also out of here. So I have a square over 2 times expected value of do you agree? I have this plus expected value of this thing. So what is the expected value of this one? It should be something easy because I am stopping here and not writing anything. So do you see anything random for this term? So, okay, 1/2 is taken out. Expected value of theta is this plus expected value of that. Okay? So I have written this. So what is the expected value of this? Cosine alpha minus beta. It's the same because there is nothing random. T1, T2, frequency, they're all fixed instants, isn't it? There is nothing random in it. You don't see anything with tilde, no random variables. So cosine omega T1 minus T2. Okay. So how about this? Now, what do you think about this? This expectation result. Cosine function, something like this, I guess. So think about it. Theta is uniformly distributed, 0 to 2 pi. This is just a constant. Frequency is constant, T1, T2, maybe T1 is 1, T2 is 2, first, second, etc. So it's exactly, but there's a minor, there's 2 theta over here because of this. 2 theta. So again this is equal to 0. Why this is equal to 0? The reason is this is constant. So I'm evaluating, if I evaluate this integral, with only changes I have 2 theta over here. Okay? So if I evaluate this expectation, I then have exactly the same calculation, 0 to 2 pi, 1 over 2 pi, a cosine, a number, plus 2 theta. Okay? If this is 2 theta, then I'm integrating over 2 full periods of this cosine, 2 full periods with respect to this theta. Okay? So it will be starting from 0 at the lower part. When it reaches 2 pi, it will be reaching 2 pi when theta is equal to pi, because I have a factor of 2 over here. It will be the same. Okay? Then, when the upper argument of this integral, upper limit, I get 4 pi. So 2 full periods. So area under just a single period is, as you see, 0. 2 full periods, 0 plus 0, it's 0. So the thing with these integrals is, sometimes they are very easy. So you don't have to do these calculations. If you know what you are doing, what you are calculating, you just write 0 over here. So what's the final result? Now I have a squared over 2 cosine omega t1 minus t2, and this is the end. This is the end of autocorrelation calculation. Well, there is also another function, it's called covariance function. I will discuss the meaning of these functions later on, but covariance function is simply, it is this, by definition. But we have calculated these mean values as 0. Both of them are 0 times 0. So this is equal to this. So I have this. So covariance function is equal to the autocorrelation function, since this process is 0 mean over here. Okay, so that is the end. So you see that the moment descriptions are very easy. So let me write, very easy to find. Let me write some notes. Number 1, moment description are easy to compute in comparison to, obviously, joint PDF descriptions, because this is just expected value calculation. Okay. Number 2, well, note that Rx, it's a little interesting, T1, T2 is equal to, let me write it over here, cosine T1 minus T2. So it's a little interesting. So this is a function of T1 minus T2. Do you see what I mean? So this is a function of 2 variables. Function of 2 variables, obviously, meaning T1 and T2. But you see that this function of 2 variables can be expressed as this. So there is another function. What is this another function? A squared cosine of the argument times divided by 2. So you see that this function of 2 variables is actually a function of a single variable of the difference of these arguments. So it's like, do you remember in high school you had f of g of things like this? Okay. So if you are computing this, you first take the difference. After taking the difference, then you pass it through this function. Okay. So you see that this is not a function of these T1, T2, even though I can select them freely over here. The function values depending on their difference only. The function values depending on their evaluation time difference. So this will be important. The form of Rx T1, T2 is equal to a function of T1 minus T2 will be important very soon in stationary process discussions. So today we will start this. So this is like a teaser for those discussions. So we see that there is something special going on for this case. So what else? Well, let me have one more note. One, two, and three. Assume theta is something like this. This is, well, 0 degrees and 90 degrees with probability 1/2 with probability 1/2. Okay? So in this case, and again I have the same process. X of t is a cosine omega t plus theta. So only difference is that not anymore it's uniform. So it's 90 degrees or 0 degrees. Here is a question to you. How many realizations do I have for this process? Well, how many realizations? Just 2 realizations, because you see that this random variable can only take 2 values. So for this one, infinitely many. Okay? So if I can calculate the mean function of this, only difference is that this time I'll be taking the expectation with respect to this variable. Am I right? At this point, I should be calculating the expectation with respect to this. So for example, let's just for the sake of discussion, let's say, let's calculate Rx T1, T2. So how would I calculate this? Well, the same story. As I have said, only difference is that I have changed this probability density function to a discrete valued, what we say, probability mass function. So this is a square should I repeat all of these steps? I mean, not so many, but should I repeat all of them? It's exactly the same. Only difference is expectation is different. So how can I take this expected value? Well, maybe I can write this one more time if I wish. So actually one of the results will be this. This will be again constant if I do this calculation. So I have from there at least this term is again coming. So I have a square over 2 cosine t1 minus t2, this part. So this was 0. Do you think it is still 0? This expected value? Let's think about that. We were discussing it. So how do you calculate the expected value, this expected value? So let me write down expected value of theta of this a square over 2 cosine omega t1 plus t2 plus 2 theta. Am I right? This is just 2 theta. I need to calculate the expected value of this. Previously it was 0 with this density definition. How about the other one? Actually, this is even easier. Why it is easier? Well, how can you calculate this expectation? Since this is discrete valued, you can calculate this. Let me call this g of theta. Okay? So you can calculate this like this. G times 1/2 plus expected value of g of theta. Theta is equal to 90 degrees times 1/2. Do you remember this? Okay. Well, this is the same as the earlier calculation. Only difference is that now this density is, if I sketch this density, it's not uniform, but there are 2 impulses. One of the impulses at 0, the other impulse is at pi over 2. And both of them have probability 1/2. Okay? I have something like this. If you want, you can think about it like that. Multiply this function by this function and take the integral. So you can see you again get this result. So what's going on? So there are only two possible cases. Theta is equal to 0, I get a square cosine this times 1/2. Theta is equal to 90 degrees, then this becomes 180 degrees, this part, okay, times 1/2. So what do I have at the end? 0. Again, I get 0. So it's very easy, I get 0. These two cancel each other. So I have a square something, and I have minus a square, the same thing. Okay, I have that. So what we have learned? Well, we have basically had some exercise on expectation calculation. We had some interpretation for this discrete random variable, what you have seen in EE 230, in terms of Dirac delta functions. But we have seen that if I do this, I can write this expectation like in the general form. So g of theta times f theta d theta. And if you write it like that, the general form, this also includes the discrete cases. So this is the thing that I sometimes mention. We use impulses also for the probability mass functions because of this property. So this is evaluated when theta is equal to 0 and multiplied by 1/2. And then this function is evaluated when theta is equal to pi over 2 multiplied by 1/2, and I sum them up. Okay, that is it. Okay, very good. So that is all. This was some more understanding of this topic. But if you are an expert in this topic, then you'll be looking at this and saying that, okay, theta can take only two values. So when theta is equal to 0, I have a square cosine this times 1/2. Then theta equal, well, 180 degrees this is. Then this becomes minus cosine. Yeah. Then 1/2, they cancel each other. That is the end. Okay. So that is the end of this discussion. Well, what else? Let me see. So also see page 20 of lecture notes for the joint PDF of Markov chains. Not in general, but of a Markov chain example. So this is the rain or shine example that you have seen before. Just read this on your own. It's not extremely critical, but if you have enjoyed studying Markov chains, okay, please also see this. It's not extremely critical for our purposes because its notation is quite complicated, so I don't want to discuss it during the lectures, but please read it. Markov chain discussion. So today's main topic is actually the thing that I have given teaser for, stationary processes. Okay? So I want to discuss stationary processes in some depth. Well, before that, I would like to remind you, do you remember the concept of steady state? Steady state concept. Well, for deterministic signals, we use the steady state concept to indicate functions or responses that reach their, let's say, final, in quotations, value. Do you remember this? There is the concept of, for example, AC steady state, DC steady state. I don't want to define them again and again. AC steady state, DC steady state. Of course, there is something else, transient, etc. Okay? Those kinds of concepts. So transient is related with the initial conditions. So the system evolves from the initial conditions towards the steady state and so on. Now I would like to have a similar description, if possible, for stationary processes. Of course, I don't say steady state process, but it will be the same kind of thing, stationary process. So let's work on a definition for random processes which enables us to extend the idea of steady state to random signals. Okay. So this part will be the most critical part. It's extremely simple, you will see. Stationarity. So I will use this part. X of t. And I have delay of, let's say, delta. This is y of t. I have said this many times, sorry for that, but tilde sometimes needed because I don't want to write capital Y like that. Okay, just my notation. So here is the situation. This is a random process. So this is just a delaying, just a delay by delta seconds. And this is the output process. I mean, this is the standard thing that you have seen in so many other courses. Just a delay operator. It delays the input by, delta seconds. So if this is a deterministic signal, for example, DC steady state, if the signal is at DC steady state, for example, if you delay it a little bit, it won't change because it has reached the steady state. In AC steady state, it's a little bit complicated, but why I'm telling you complicated? Because it's the cosine function. The argument of the cosine function is, omega t plus theta. You see the same cosine function after some time. Okay. So how can I extend such ideas to random processes by related with the delay? So stationarity requires the statistics at the output, this is the output, and input to be the same. But there is a critical thing for all delta values. Okay, for not a specific delta value. For delta is equal to 0, I mean, they are the same. But it should be valid for all delta values, however delta is large. So that is the idea. So if this has reached somehow stationarity, maybe you can think about it from Markov chains. So Markov chain starts from a point. Now it reaches stationarity. If it is reaching that stationarity, if you delay it, if you look at it at a later time, it still has the same steady state, let's say, behavior or stationary behavior. So how can I right now apply this? So let's see. Stationarity we should study this a little bit. Joint PDF description. Number 1. First order PDF. First order PDF description. Okay. Now what do I have? So this thing, let me draw it very briefly. So let me write it like this. This is the impulse response of this system. So I have x of t. I have y of t, which is xt minus delta. Okay. Now, first order PDF description. So it says that stationarity requires the statistics at the output and the input to be the same. So what does this say? If you look at the input statistics at time t1, okay, this is the density at that time. It should be equal to the output statistics at time t1. So I'm writing over here, I should have write y1 over here, but since this is an equality, I'm using the same variables over here, x1. Okay, do you understand? Of course, this is the y process. Y process evaluated at time, this is a y random variable. So for example, if this is a Gaussian distribution, this should be a Gaussian distribution. Okay? So this is the variable of that Gaussian distribution. So it also says that this distribution's peak value, if it is Gaussian, the mean value, variance value, it should be the same. So, but I know also the following. This is nothing but let me write here then generic variable x, because it's confusing us these times. There is only one variable x. So this is, if this is this, this is this. Because you see that y at t1 is equal to just x sample at a later time, okay, at another time. So it's interesting. So let's forget about this part. This equality is interesting. So this tells us that if I calculate the density at t1, in other words, if I look at the random variable by the sampling of the process at time t1, and if I look at the random variable by the sampling of the process, let me call this another time, t2, they should be the same. Okay? For example, there is a sample space. There are many random, let's say, realizations like this. This is the black realization. This is the blue realization, etc. Like in this case, we have two realizations. Let's say we have two realizations over here also, black one and the blue one. So you look at this, okay, at time t1, you see a distribution, okay? At t1, I can have this value or that value. At t2, I can have this value or that value, as you see. So if this is stationary somehow, what do I expect? So wherever you look at, you should see the same distribution. Okay? Whenever you look at, whenever you evaluate this random process, you should see the same distribution. So let me give an example for this. Example. Actually, we had two examples, random slope signal and random phase cosine. So what was this? This is x of t, a times t. This was x of t, a cosine omega t plus theta. So this was like uniform 0, 1. This was uniform 0, 2 pi. Okay. So what was the first order description of this? So let me write this. It will be easier. When you evaluate it at t1, this is the x1 random variable. What is the distribution of this? Well, it is uniform in 0 to, well, a is 0 to 1. If you multiply this by at time t1, it can go up to t1. The minimum can be this uniform t1. So if I evaluate at another time this random process, so the first one is, let's say, this time, at another time, this is uniform at t2, 0 t2. So for example, this can be uniform distribution, t1 is equal to 5, t2 is equal to, let's say, 6. Okay, so this is the density, uniform distribution. This is the uniform distribution. You see that the density changes by time. Density changes by the evaluation time. So density at time 5 is not equal to the density at time 6. Okay? That is the issue. So how about for this one? So this is not first order stationary. Not. Because density is changing by time. So for the stationarity, statistics should be the same at different, at T1 and at T2 evaluations, it should be the same. I should get the same density. So how about this one? So this one was a little bit more complicated to write. Let me see. This is like 1 over pi. Okay. So this is the density that if we sketch this, I have sketched at the beginning of this hour. It's this one. It has singularities at x1 is equal to a and minus a. So this is this sketch. This value is 1 over pi times a. This is a. Okay. Something like that. Okay. So do you think, do you see a t variable over here in the definition of this density? There is no t. So if I evaluate it at t1, I get this. If I evaluate it at t2, I get this one. So you see that it's the same density. So this is first order stationary. Okay. So we have first order stationarity for random phase cosines. Two different type of processes. This is not stationary. Actually, this is getting, spreading in time. You may think about it like that. This is always the same. If you look at it at another time, you always see this distribution at different times. Okay. So this is good. This wasn't that difficult. So this is again a classification of, PDFs according to this kind of a property. So I see that my earlier example number 1 does not satisfy this property, but the second one, random phase cosine, satisfies it. So this is more like a classification of my earlier results. But you will see that this will be very important for us. Because such operations, like delay operations, are basis of signal processing, isn't it? Linear time invariant operations. Okay, but let me do the following. Since we have started, number 2, second order stationarity. Okay, now again, let's draw the picture, x of t. I have y of t. This is xt minus delta. Random process, random process, random process, just another sample. I'm just changing this t definition essentially. Okay. Well, what should I write? Okay, let me write the following. At the input, I see this kind of a distribution. Let me write here x1. Sorry, because this is not the density. I have this. 2 evaluations times. This is the input. Now at the output, I have y1. y1 evaluated at t1, but okay, let me write it. y2, this is this process evaluated at t2. Output process evaluated at t2. Okay. This is the random process. But by the definition, I know that this is the input process, t1 minus delta, t2 minus delta. So what is the requirement for stationarity? I haven't used anything right now. Input process is x. Forget about this connection. There is another process called y. I sample it at the same time instance. So if there is some stationarity, now this claim. The second order statistics, their joint PDF. Joint PDF should be the same. If the process x of t is second order stationary. Okay. But this should be also, again, this should be valid for all, remember, for all delay values, for all delta. Okay. So how can I deal with this? Let's erase this part. Well, I can deal with it by writing this. Let's see how I can have that. Well, let's go over here. Then the density, joint density, let's say first random variable, second random variable, should be equal to the joint density of these two, different times. Okay? So how can I have that? I can write y over here, but at the end I will make a crossover that one. I will think about the property of x to have that. So again, in order to have equality of these two sides, left side and the right side, I should have the same variables. So this corresponds to this corresponds to this. In other words, this is the random variable's name, and this is its variable. Okay. So, but in critical thing is, this should be valid for all delta. So how can I have that one, or what kind of relation is that? So previously, we had only one of them, like in the first order case. Do you remember? In the first order case, I have a function of x1. I have another function of x1. This is generated at a different time. So this is second order. I have two functions like that. So the issue is, let's look at the special case of delta is equal to T2. Then what do I have? Then this is equal to this should be equal to then T1 minus T2, x1, x2, x of 0. Am I right? If delta is equal to T2, let me write the delta bigger. So this is just a special case, as you see. So when delta is equal to T2, I substitute over here. If the process is indeed second order stationary, it has to satisfy this one. So what kind of function is this? So we see that this is just a function of, so you don't see T1, not a function of T1 and T2 independently, but this side, a function of T1 minus T2, okay? T1 minus T2. Well, you see something like that. So what's going on? So how can I have a result like that? Again, let's sketch this sample space. There is a random process realization. There is another random process realization. Okay, there can be many other realizations. Now, this one looks at two time instance, T1, T2, okay? The other one, this one, looks at two different time instance, but you see that they are just shifted by the same amount, delta. Okay, for example, if I shift towards this side, let's say, for the sake of simplicity. So this is, let's say, T1 minus delta. This part is T2 minus delta. So it says that you have this two evaluation times, T1 and T2. Okay? This is this. But it says that you have a joint distribution of these random variables at these two evaluation times, this side. It says that you can select this delta freely, then any other evaluation times, T1 minus delta, T2 minus delta. So over these green lines, I establish these random variables. Joint PDF establish over these two green lines equal to the ones over this red line. So these are different random variables, but they have the same PDF. If this is somehow Gaussian, this is also Gaussian. Gaussian has a mean something, the same mean is over here, etc. Okay? So since you can shift this towards right by changing delta, so what is being preserved? Only thing that is preserved is the distance between them. So this, as you see, this distance is the same as this distance. So this is the same as this distance. Because as you see, I'm just shifting these evaluation times by constant delta to the right, to the left, but it's always, this one is shifted over here, T2 is shifted over there, and that is it. So their distance is the same. Actually, this is that observation. So it says that now everything depends on the distance between T1 and T2, evaluation time distance, if I have something like that. So let me write it as a sentence. Let me erase this. Maybe I can use this one. The stationarity in second order joint PDF requires that the joint PDF function should only depend on delta t, let's say T1 minus T2 value. In other words, f of T1, f of T2, x1, x2 is given. Let's say this is equal to f of T1 plus 5, x of T2 plus 5. This is like that. So let's say that you know this density, but somebody asks you, how about the density at, T1 plus 5? T1 is equal to, let's say, 1, T2 is equal to 2, for the sake of simplicity. You know, if you have found this density. If the process is stationary, this was 1, this was 2, this is also the density at 6 and 7, okay? If the process is stationary. At the sixth, so the first one is 1 plus 5 is 6. At the t is equal to 6 and t is equal to 7, you have different random variables. But the interesting thing is that this is just the station, because the concept of stationarity means if I delay my sampling instances by the same delay amount, nothing should change. Okay? So if I delay my sampling instance like this delay box by 5 seconds, if I start this experiment 5 seconds later, okay, then I'll be getting these two samples. But since the process is already in the steady state, it requires that they should be the same. Of course, this is not limited to 5. This is limited to for all, you may say, this kind of offset values. If I shift it by 10 seconds, if I shift this by 20 seconds, and so on, I should always get the same PDF. So this is the meaning of this. So conceptually, these things are a little bit difficult to even express, write these equations, but The difficulty is essentially in the notation. The concept is quite simple. It's the extension of steady state. If I collect my samples at the steady state over here or at the stationary process, when the process is stationary, over here, if somebody collects samples at a later time, it shouldn't be making a change because the concept of stationarity requires this. Okay. So let me write one more thing. This is f of just one more example. 10, just to emphasize this, plus 10 is equal to this. Or actually, this is my, in this case, minus delta. Minus delta is minus 10. Yes, delta is minus 10. Okay, that is that. So I'm just evaluating these two samples by some offset, you may say. I may have an offset in my sampling time, but it doesn't matter because these samples are at steady state. Well, let's see. What else do I have? Let me write a comment. Note, random phase cosine is an example for second order stationary process. So it's an example for, I will say more things about this. This is just an observation right now. But let me see. If I keep doing this, now I want to write something about number 3, nth order stationarity. Okay? First order, second order, nth order. Now, what do I mean by nth order? I think you get the idea. If I have n samples collected somehow at different time instants, and somebody gives me their joint PDF, very good. So nth order stationarity requires that if there is some offset, common offset to the sampling times, do you see this? Well, just 2 of them. Now I have n of them. Okay. So the way I feel about this, like maybe this is like you may find it like an irrelevant example. So the absolute time is not important, as you see. The absolute time is not important. Only the difference between these samples. For example, you are living for a very long time, so time does not matter. Maybe you live up to infinity, so you always think what will happen in the next second. But it doesn't matter when you start that thought. So you can start that thought at t1. So only difference is the difference between these two. The difference between events. Time difference between events are important. Okay? It doesn't matter when you start, whether you collect your observation at this time or that time. Only the difference between t1 minus t2. The second sample S has t2 minus t1 difference. Okay? It's sampled at the time difference of t2 minus t1. Similarly, this one is sampled at the same time difference. Okay? This is the concept of stationarity. Okay, so we will continue from this point. Well, important thing, this should be valid for all delta one more time. This is the critical thing, all delta. We will continue from this point on after the break of 10 minutes.